All right, good morning. Here we are again. It is now time for yet another lecture of CENG 3306 Mechanics and Materials. I hope you all had a chance to review the lecture from yesterday because we're going to need it. All right, so today we're going to be talking about Mohr's circle, and we have a few learning objectives today. One, we wish to know how the equations can be manipulated the equations of stress transformation can be manipulated to form the equation of a circle. We wish to develop Mohr's circle for stress at a point and use the circle to determine the principal stresses, max in plane, and stress acting on any plane. So let's do all that. All right, so first of all, let's do a review of general loading. Here. Let's see, review of general loading. Of general loading. All right, so we need to remind ourselves of our equations of stress transformation. So consider an arbitrary member with an xy axis, x being along the axis of the member, y being perpendicular to the longitudinal axis of the member. So consider, and we're not just looking at a CAL member. We are looking at a member with arbitrary loadings placed upon it. So don't worry about drawing those at any kind of exact angle. I'm just trying to show an arbitrary member with arbitrary loadings. We have an x and a y axis here. All right, and then we can also find, so we have the member here, but then we can also find we also know how to already find the state of stress at any angle of rotation theta. In other words, we can cut this member at any angle theta and find the state of stress therein. And so please see the previous lectures for developing the equations of stress transformation. And also the book has some very good derivations of those formulas. So we have here, shear stress here, and shear stress here, and our two axial stresses, our two normal stresses. So we have the stresses, in other words, we start with our stresses in the xy axis here, and we wish to be able to find them at a rotated axis, x prime and y prime. And that x prime, y prime is again at a rotated axis. Oh, not yellow, let's do green. At a rotated axis like shown. So we have a shifted or a rotated x prime and y prime, and this is rotated a certain angle theta. Anyway, so we have the equations that we developed previously. Let me write some of those out. So our normal stress at any angle, sigma x prime, is going to be, again, the equation sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times the cosine of 2 theta. And addition to this, plus tau xy sine 2 theta. Sine of 2 theta. And tau x prime y prime then is going to be negative sigma x minus sigma y over 2 times the sine of 2 theta plus tau xy times the cosine of 2 theta. And these are the equations of stress transformation. And then the equations for the principal stresses, sigma 1 and sigma 2, in other words, the maximum stresses present at any plane of rotation, or any angle of rotation, I should say, any cut plane, any angle of rotation. Sigma 1, sigma 2 are going to be sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy quantity squared, like shown. And as a reminder, we can note here that this term here is equal to the tau max, the maximum shear stress. And this term here is equal to the average normal stress, sigma average, ABG. And then also we remember, all of this stuff is from previous lectures. We also have the angle of principal normal stress, theta p, 1/2 inverse tangent of tau xy over sigma x minus sigma y over 2. Inverse tangent of all that. And also the angle of maximum shear stress is going to be 1/2 the inverse tangent of, let's see, we have negative, let's see, actually, yeah, sigma x minus sigma y over 2, all of this over tau xy, as shown. Let's see. So this allows us to know what angles that sigma 1, sigma 2, and tau max act on. Oh, I guess I missed slide 1 on here. Oh well, whatever. It's fine. Just a blank sheet anyway. Okay, so what we want to do is we want to okay, backing up. You notice we have a lot of thetas here. We have a lot of sine of thetas. We have a lot of cosine of thetas. We have a square root of a sum of squares. I've done a lot of pre-calculus. I've done a lot of math over the years. This looks a lot to me like there might be an equation of a circle hidden in here somewhere. And in fact, there is. That circle is known as Mohr's circle. And we're going to first develop the equations of Mohr's circle. So let's do that. Development of the equations of a circle. Of equation of a circle. So what we're going to do is, the general approach here, we are going to square and sum sigma x prime and tau x prime y prime here. So sigma x prime minus sigma x plus sigma y over 2 quantity squared plus tau x prime y prime squared, and all of this will equal sigma x prime minus sigma y. Oh, sorry, that's not prime, that's just sigma x, sigma y. Sorry about that. Sigma x minus sigma y over 2 squared plus tau xy squared. And essentially what we can say here is that the radius of the circle squared, r squared, is equal to tau max squared. So in other words, the radius, the magnitude of the radius, is equal to the magnitude of the maximum shear stress. Okay, So I know the equation of a circle. The standard form of the equation of a circle is, okay, so we're going to have something like this, an x and a y axis. However, this x and a y axis is going to be a plot of the shear and normal stress. So let me put a little arrow here. So we're going to have on this axis sigma x prime, and on this axis tau x prime, y prime. And then along this, we're going to have a circle C of some sort, and the center is going to be along the sigma x prime axis. Okay. And why is the center of this along the axis? Because we remember from previous lectures that the maximum normal stress is going to occur, the maximum and minimum normal stress is going to occur at a location where the shear stress is at a minimum, or sorry, the shear stress is actually 0. So when the normal stress is at a maximum, that's this point here, or at a minimum, this point here, the shear stress is going to be 0. So we can actually see that this circle is going to be, the center of this circle is going to be at some point along the sigma x prime axis. So essentially, we are plotting normal versus shear stress, using the normal as an x-axis and the shear as a y-axis. This is why they made you take all that math before you got into this class. Remember when you were taking pre-cal and you thought, man, I hate the equations of these conics. I'm so glad I never have to see this stuff again. Guess again. Not today. Sorry. All right, that's a little evil. Okay. So y minus b squared equals c squared. This is the general equation for, this is the standard form or the general form of the equation of a circle. If we want the equation of our specific circle, all we need to do is solve for constants a, b, and c. So let's see. The equation of a circle. So we want the equation of a circle in the sigma x prime, sigma or tau x prime, y prime plane. Tau x prime, y prime plane. The center is at sigma average, comma 0. Because you remember from a previous lecture, we saw that the average normal stress is going to be just the numerical average of the minimum and the maximum. So the center is actually right at the, oh, did I write theta? That should be 0, sorry. The center is right at sigma average, comma 0. And then this is also equal to, we can say, the sigma average is sigma x plus sigma y over 2, comma 0. And this is found on page 35 of the FE exam packet, if that's needed. And the radius of the circle is going to be simply sigma x minus sigma y. Let me write this a little bigger, I think. The radius of this circle is going to be, oh, maybe I don't need the brackets. Yeah, it's going to be equal to tau max, but it's also equal to sigma x minus sigma y over 2 quantity squared plus tau xy squared, which is also equal to tau max. So in other words, the maximum shear stress gives us the radius of this circle. Okay. Got that? Okay, good. So Mohr circle for stress, the geometric solution. And there's also a circle for shear. It's not for stress, but not for shear, sorry. Just like we have one for stress, we'll also have one for strain, which we'll get to in another lecture. Mohr circle for stress. Geometric solution. So, what is this? It is a graphical representation representation where each point on a circle represents the state of stress on a plane through the point in question. Where each point on a circle represents the state of stress on a point in that circle, or on the point in question. So by graphing the circle, we will have a complete representation of the state of stress at any possible orientation in question. Okay, so sign convention. What will our sign convention here be? Well, it's going to be very similar to what we've done before. So let's talk about normal and shear stress. Normal and shear stress. So normal is fairly easy. This is just saying that tension will be positive and compression negative. Shear stress, we're going to use the convention clockwise is positive and counterclockwise is negative. So in other words, what I mean by that is like this here. If you have a stress block here, 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 and here, we have these individual stress arrows, and let's see, this one would be negative because it's counterclockwise. This one will be positive because it's clockwise, and so on and so forth. Okay. Note, this is just the this is only the sign convention for plotting on Mohr's circle. Do not confuse this with positive state of shear stress. I'll put a big note in red. Do not confuse with positive state of shear stress. The positives in the normal state of shear stress is positive state of shear stress. The positive state of shear stress is when you have something like this. So we say this when we have when you have a system like this, we say that we are in positive shear. The when you have the Mohr circle, if you have a shear stress above the axis, that means you have a shear arrow here or here, and below the axis here or here. So definitely read up about that in the book for further explanation. Got that? Okay. So let's talk about the mechanics of it. How do we actually create it? What we might call the mechanics of Mohr circle. Mechanics of Mohr circle. So we start with the state of stress. Our sigma x, our sigma y, and our tau xy. That's what we start with. 2, we plot 2 points representing stress on two orthogonal planes. Orthogonal has an O, not an A. Orthogonal planes. 3, our stress block theta, the theta of our stress block is equal to Mohr's 2 theta. So in other words, if we have an angle of rotation of 45 degrees here, we'll have an angle of rotation. If we have an angle of rotation of say 15 degrees here, we'll have on the Mohr circle, we'll have an angle of rotation of 30 degrees. It's whatever the angle of rotation here, you double it when you actually plot it on Mohr circle. Okay, so 4, we sketch the circle. And to do that, we need a few things. We sketch the circle just by taking the 2 points. We basically just plot 2 points and draw a circle around them. Then we locate the center using sigma average equals sigma x plus sigma y over 2. Determine radius using r equals etc., etc. Determine radius r using it's essentially just the Pythagorean theorem. Just our old buddy Pythagoras. Pythagorean theorem. And that is just what we had earlier. R equals, if you look at this, if you look at the 2 points, this is basically just the distance formula between the 2 points. So sigma x minus sigma y over 2 squared plus tau xy squared. And finally, 7, we can get our principal stresses. Sigma 1 is going to be sigma average plus r, and don't worry, I'll work through some examples of all this nonsense. This may seem like total nonsense, but we'll get it, don't worry. Sigma average minus r and tau max is equal to r. All right, questions on that so far? Okay, good. All right, so let's see how to actually work with this beast. So I'm going to give us a state of stress, and I want us to find Mohr circle, and to plot and to find the principal stresses. Okay, let's see. Yeah, we're good there. Okay, so let me work through an example. This will definitely be a rather long example. That's okay. And first, let me make sure we're recording. Yep, we are. I'm always going to be, after that first day, I'm always going to be super paranoid. So I apologize for those of you watching closings of the program to make sure my software is recording. All right, so example 1. example 1. So we are going to have the following state of stress at a point. So we don't have any idea what kind of system this could be. Maybe this is a beam, maybe this is a column, maybe this is something entirely different. I don't really care what it is. All I'm telling you is that we have this kind of state of stress um, at a single point, and we wish to find some other things. So I tell you this. I tell you that at this point, we have a sigma x here, a sigma x of 1400 psi. Oh, sorry, I wrote those in the wrong direction. I want this to be in compression, sorry. And I have a sigma y in tension of 1000 psi. And then I have shear stress, tau xy, like this. Now, you may notice this is going to be negative. So tau xy equals, actually we say 500 psi. But that's as drawn. What these actually mean are, if I get the numbers that I'm going to actually use in the circle, sigma x is of course going to be equal to negative 1400 psi because it's in compression. The tau xy, and these are what we're going to use in the formulas, will be negative 500 psi. And the reason for that is that this is a state of negative shear stress. It is going opposite our standard sign convention for positive shear stress. And sigma y is positive, and it's 1000 psi. All right. Now, fundamentally, what we have here are 2 points. We need 2 points, and those points are going to be, let's say here, this can be point 1. Let's look at this. We can have our first point might be represented by this one, and basically we form our 2 points based on our, we could do it in many different ways, but really any 2 points will do. So let me just pick 2 points, for instance. Maybe one horizontal and one vertical is usually pretty good. So I'm going to use this one and this one. This point is 1000, comma, negative 500 for a horizontal point. And maybe for a vertical, this one will be negative 1400, comma, 500. Okay. Remember when we said here, do not confuse with positive state of shear stress? Negative shear stress on the Mohr circle is positive shear stress is clockwise. See, this one will have a positive shear stress. I'm forming an ordered pair based on this normal stress and this shear stress. I'm looking for an ordered pair. Like this thing is going to go with this thing would go with this would go with this, etc. So this is a positive shear stress only in terms of the Mohr circle. I call this arrow a positive shear stress because it's going clockwise, and this one negative because it's going counterclockwise. Hopefully that makes a little sense. I know this can be very confusing, and the sign convention always trips people up because they're seeing, okay, why are we looking at the shear stress positive, negative for a single one of these shear arrows instead of the entire thing? I know that's a little bit confusing. You will have to spend some effort to really nail it down. Okay, what else? Okay, so you were given all of this. Well, you weren't given the 2 pairs, the 2 ordered pairs. We found those. But I forgot to tell you what we need to find. We need to find what we were given was just the stress block and sigma x, sigma y, and tau xy. We want to find we want to find sigma 1, find sigma 1, sigma 2, tau max, theta p, and theta s. Solution. All right, so we're going to need a few equations. We're going to need our equations that we developed before. So let's use those. Let me first write the equations that I'm going to use in red. Sigma average equals sigma x plus sigma y over 2. And I'm going to use the radius equation, which is just the distance formula, square root of sigma x minus sigma y over 2, quantity squared, plus tau xy squared. And then I just plug in numbers, or substitute in numbers if we use the proper mathematical language. Negative 1400 psi plus 1000 psi over 2 equals negative 200 psi. All right, and this is then equal to the square root of negative 1400 minus 1000 over 2 squared, pardon my chicken scratch, plus negative 500, and all of these are in psi, squared, and this comes to 1300 psi. Huh? Oh, sorry. Okay, sorry, 1300 psi. Okay, so we now have everything we need to define the circle. We have a sigma average, which is our the center of our circle. It's going to be the center is going to be located at negative 200, 0, and the radius of the circle is now 1300. All right, so next let us find the principal stresses, sigma 1 and sigma 2. So I want to find principal stresses. Sigma 1, sigma 2. And so let's see. Sigma 1 is just going to be sigma average plus R. And sigma 2 is going to be sigma average minus R. Which is equal then to negative 200 plus 1300, which will be equal to 1100 psi. And this is negative 200 minus 1300 equals, then this equals negative 1500 psi. And these will be our principal stresses. In other words, this will be our maximum. The 1100 psi will be the maximum normal stress we will ever see at any plane of rotation, at any cut angle at this point. And sigma 2 will be the absolute minimum normal stress we will ever find. Although we could start talking about what do we mean by maximum and minimum. If we were talking about actually absolute value, this would be the maximum and this would be the minimum. If we're talking about positive, negative, this would be the maximum and this would be the minimum. But that's just some mathematical parlance. All right, next, let me get the principal angle, theta p. Okay, so remember the Mohr circle angle is Mohr circle theta is going to be twice the shear, this is twice the previous angle that we found, theta p. So we use 2 theta p to represent the Mohr circle one, equals the inverse tangent of 500. Actually, let me go back. Let me show you where this is coming from. Here, where did that? Right here. Oh no, sorry. This is the untransformed one. Sorry about that. This is just the original. This isn't yet shifted for Mohr circle. This one half is already there. 500 psi over 1200 psi. So I lied to you. I'm sorry. And this leads us to that theta p equals 11.3 degrees counterclockwise. And this is the actual physical angle of rotation. The Mohr circle one will be different than this. Okay. So we have, in other words, we now have our principal stresses, our principal normal stresses, and we have an x prime. I could draw this as an x prime and a y prime, and we'd have a stress block like this. There would be no shear stress on this at this orientation, because at the principal angle, the shear stress is 0. So we would have 1500 in compression and 1100 in tension. PSI, of course. Now, let us find the max shear stress and its angle. The maximum shear stress and its angle. All right, so here, tau max is equal to R, which is equal to 1300 psi. And sigma average, again, is negative 200 psi. Now, we can use this equation here that we've worked with previously. 2 theta s, oh, that looks really bad. 2 theta s equals 90 degrees minus 2 theta p, which is then equal to 90 degrees minus twice 11.3 degrees, which is 67.4 degrees. That's what 2 theta s is equal to, which means that theta s is equal to 33.7 degrees clockwise, not counterclockwise, clockwise. And you got that? Okay, let me just draw the stress block at the point of maximum shear stress. Here we would have x, and let me show a shifted axis, y prime and x prime. Here we would have this here. Now, the normal stresses for this is, let me just first label. This is 33.7 degrees. Like this. Now, the stresses on here are going to be, each of these is going to be 200 psi, all in compression. At the point of maximum shear stress, the theta x, the sigma x and sigma y are both equal, and they're equal to the average, which is the negative 200 we got before. let's see. So like I said here, is negative 200 psi or 200 psi in compression. So 200 psi, 200 psi, 200 psi, 200 psi, and the shear stress is going to be negative here. So I'm going to draw it as a negative orientation. And this is negative tau x prime y prime equals negative 30. Or I'll just actually, as drawn, I already drew it negative, so I'm not going to put a double negative on there. I'll just say it's 1300 psi. So we did all that, but we don't actually have a circle yet. I've been talking about circles, but I haven't actually found one yet, but that's okay. We'll get there. I promise I actually will draw a circle at some point. Okay. Now there is another location of maximum shear stress, and that would be another way to get another location of maximum shear stress is going to be 90 degrees away. This one is 33.7 degrees down from below the x-axis. Another one would be 90 degrees clockwise from that, or 90 degrees counterclockwise from that. So the other maximum shear stress would be here. Option 2 is going to be like this. There will be two locations of maximum shear stress. And so this is the x-axis here. Let me erase that other line. This will be x prime and y prime. And here, and I know that is a very mutated square, but oh well. It's sort of Friday. Last day of the week. Well, for the summer anyway. So the normal stress is again all going to be 200 psi in compression. And we're going to have basically the same, this is basically the same block. It's going to be negative shear stress. And this is tau x prime y prime equals, again, it equals 1300 here. It's negative 1300, but I have it drawn as, it's already drawn as negative, so I'm not going to redraw that, or call it a negative again. 1300 psi. And the angle of rotation of this oh my gosh, that is a very bad square. Oh well, it's a square. It's squarish, sort of. 56.3. 56.3. 56.3 degrees. Okay, so we've completed part one, finding the state of stress at that point. Now, what if I have the equations of Mohr's circle, but I wish to find the state of stress at a different point, or at a different angle, at a different point, a different angle? You got that? Okay, good. So we completed part A, which was to find the principal normal stresses, the max shear stresses, and the critical angles. Then B, I'm tasking us with find the stress on a plane AA, which I'll define. On plane AA, which I'll define. So first, let me show you where plane AA is. Well, we have our original unshifted stress block, our unrotated vanilla plain ordinary stress block. of 1400 psi, like here, and 1000 psi. Here, and here, and here, and here. 500 psi. And the angle of rotation here, that we're basically, we have this is the initial stress block, and I want to find a particular angle for whatever reason. I wish to find the state of stress on plane AA, and plane AA is at an angle of, I'm going to call this theta A, and theta A is, let's say, 36.9 degrees. So theta A is 36.9 degrees. 36.9 degrees. Now, do you remember when I said that, let's see, that the angle in the actual Mohr circle is twice the angle of the physical angle? So, solution, what are we going to do with this? Solution. Rotate 2 theta A from H. H is this one here, the horizontal. See, remember we defined back here, well, let's see, this one is H. Well, we're going to be 2 theta, we're going to be 2 theta A from that. Okay. So let's look at this. From H. Let's see. So in other words, we're looking at 73.7 degrees counterclockwise. Okay. So if we do some trigonometry, if I make a triangle, let's see. In other words, if I have this here, so remember, let's look at the points here. This is the center of the circle is at 0. Not the center of the circle is not at 0. Sorry, let me go back here. But I do have point 0 here. That's not the center of the circle though. 0, negative 200. Where? Just a second. Negative 200. Okay, gotcha. That's the average. Sorry about that. That's the average stress. This is the center of the circle. Negative 200. So I need to rotate a certain distance there. Here. This is R. This is R cosine theta, and this is R sine theta. And theta is equal to 73.7 degrees minus 22.6. This is a different theta now. This theta here inside this triangle, which is equal to 51.1 degrees. I know this can be confusing at first. You may have to read the book to really reinforce this. Sigma equals 1300 psi times the cosine of 51.1 degrees equals 816.35 psi. Then if I subtract, but this is, then if I subtract 200, see, R cosine theta is just this part, but then if I want the overall, the actual sigma here, I have to subtract minus, I subtract 200, which comes to 616.3 psi. So that's my sigma stress here, my normal stress here. Then I can also say, oh, sorry, did you get that? Okay. I can also say that tau is equal to 1300 sine theta, or sine of 51.1 degrees. Don't need to do any subtraction here. It's just 1013 psi. Oh, that looks really bad. Oh, I erased everything. Tau is equal to 1300 sine of 51.1 degrees. We still have this right. Good, good. I was worried. Equals 1013 psi. And that's our shear stress at this point. All right, so if I draw the stress block of this system, then I'm going to have this. X, I am going to have an angle of rotation x prime, y prime, an angle of rotation 36.9 degrees, a stress block that I'll try to draw reasonably square this time. Better. This is then like this, like this, like this, like this, and then this is going to be negative, or sorry, positive actually. So this is 1013. This is 1016.3, and this is 616.3 psi. And that's the full state of stress. Okay. Alternately, we could also use a different triangle. Well, another way to think of that is in order to get not a different triangle, but the in order to get the other one, we can think of it like this as well. Every plane through a circle will have two different triangles we could make on it. So we could also look at, say, 51.1 degrees here. 51.1 degrees here. This would be r cosine theta, r sine theta. And this point, okay, let's see. This point here would be a stress of negative 200 psi, and a normal stress along the, this is along the x-axis, and a point, the center again is negative 200. And this, the coordinate of this, the bottom coordinate here, which is the real coordinate that we're looking at, is this is the coordinate of most importance, or it actually shows the stresses there, is negative 1016.3, comma, negative 1013. So that would be the other location that we could look at.
So how do we determine which of those two stresses, the 1016 or the 616, which of those is the x versus y, x prime versus y prime?
Okay, let's see, the x prime versus y prime.
Or is it just is it kind of arbitrary?
It'll actually come out of the circle. It'll come out of the circle is where you figure out which one is x prime and y prime.
That kind of makes sense. So
yeah.
I mean, I can see. I mean, it follows that you're just shifting the original.
Exactly.
Stress block.
Yes.
But I mean, if I'm just looking at the numbers straight out of nowhere, I mean,
yeah, you like to trace through the stress block and follow through the circle.
Right.
Okay, so let me show you what the Mohr circle on this one actually looks like. I promised I would actually draw at least one circle today, and I'm going to do that. So, let's see. I'm going to have another example I can work through. Yeah, that'll be good. So say we have I'll plot um, the sigma x, or the sigma and tau axis. So this is normal stress. Let me not even call it necessarily x. Let me just call it yeah, sigma and tau. Normal stress and shear stress here. So the center of this circle is at negative 200, negative 200, comma 0, negative 200, comma 0, and the circle is, well, like shown. Oh my gosh, that is a really bad circle. Wow, okay. Yeah, there's no such thing as a good circle. Okay. A perfect circle, like I always draw. Okay, perfect circle here. And the radius of that would correspond to the radius we saw earlier. I think I have another example that I want to work through that will actually use the circle a bit more, hopefully. Now, to really do this accurately, really the whole point of Mohr circle is it is an early tool that it's very useful if you actually are willing to graph it properly. In order to actually use it as a graphical tool, you would literally have to graph it properly. You'd have to use a ruler, and a compass, and a protractor. It can be done, but it's a graphical tool. In order to use graphical tools, you need to actually graph them accurately rather than just sketching them, which is what we're doing here. So here, and this is the state of stress that we had initially. I'm just going to show this on here one more time. Of like this and like this, of 1400 psi, 1000 psi, and 500 psi. All right. In fact, I might pause the recording quickly and make this a part 1 and part 2 here.